Where we ended Monday is we got the double bond, and we said that was pretty cool because that starts to match a piece we've got there. And the thing we also noticed was that if that piece was indeed the one in our final product, we need reactivity at that carbon, right? This carbon needs to be reactive. What did we say was the problem with making that carbon reactive? I don't know what not stable means. Give me information about that carbon. What do you know about it?
sp3.
It is sp3 hybridized, which makes it an alkane functional group. What do we know about alkane functional groups? They don't react. In fact, there is only one way to get alkane functional groups to react, and that is radicals. We have to use radicals. So we're going to be going through some kind of radical mechanism to get that to happen. Okay. When we're dealing with our radicals, there's really only 3 reagents, I believe, if I got it right, that I want you to remember. Br2 and light, which is going to do what? Attach bromine. Okay, but now the question is, where does it attach bromine? The issue with Br2 is, what does Br2 react with? With alkenes in an addition reaction. Do we want it reacting with the alkene? No. So throwing Br2 and light here in this reagent is probably not the best option, okay? Because it'll likely compete and do the addition reaction and the alkene and the radical reaction. Okay, what's another reagent? HBr, good guess. HBr also does an addition reaction. We don't want that. Okay, all we want is a halogen coming in on this. Br2 is our option to react with alkanes, but we want it in very limited concentrations. The best answer is, that's a hint. There, I heard it, NBS, N-bromosuccinimide, which will supply a very small concentration of bromine, giving us the allylic substitution. Okay. What has this now done for us? Well, we've got this piece, okay, where this carbon is what charge? Keep using that color. Let's switch to purple. That carbon is what charge in our piece right now?
Oh, it has a partial positive.
It has a partial positive charge. Why?
Because of bromine.
Because of the halogen. Right? If I look at the other piece I need to supply, what charge would I expect that leading piece to come in as?
Negative.
Negative. Why?
Because you want to attach that carbon.
Because oxygen, very electronegative, very likely will come in with electrons. Getting a positive oxygen is not particularly easy. Right? So I have half of my problem solved. Okay? One of the stipulations that we threw in this, though, was that we can only use our, what is that, bromo-isopropane as our starting material, or our starting carbon source. And so we have to bring in more carbons. We're going to stop our synthesis with that leftmost piece, because we've got that piece. What do we now need to find? The right side piece of our answer. We know we have to start with this. And somehow we have to get up to this guy. Okay? Where's the chemistry in our product piece? Where's it located? We're looking at our product, that black box. Carbon, I accept. Which carbon? Next to the oxygen. Keep going. More descriptions.
Partially.
Yep, it's partially positive. Where is that carbon? Terminal. It is at the end of our carbon chain. If we take a look at our starting material, where's our reactive carbon? In the middle. What do we have to do? We have to somehow shift the reactivity. How do we shift the reactivity? Same thing we did previously. We have to go through an elimination reaction. Okay, so we could set this up with some heat and a base. And we can now get our double bond like that. Closer. We now have reactivity at that terminal position, but we still have reactivity at the internal position, and I don't want that. Okay. If we kind of simplify, what I'm aiming for is roughly something like that.
You need an addition.
I need to do an addition reaction, or what am I adding?
An alcohol and then I said
An
oxygen.
OH and hydrogen. What reagents add hydrogen and OH? Water is a really good guess. So let's throw water in there. Okay? The alkene is not particularly reactive. Okay? So even if I throw water at it, I'm not going to get a reaction. I need something to catalyze and speed that reaction up. I could, not quite. Acid. So we add acid, say H plus, and water. Okay? And here's where one of the complications comes up with our synthesis. What are we saying is the result? That's what we want to be the result. Does that mean that is the result? Okay. Where did the hydrogen go in that product?
Hydrogen in the product above.
It went to the more substituted position. When we add hydrogen under acid catalyst, where does the hydrogen go?
It's going to go into your thermal.
It goes to the least substituted. This reagent doesn't work. It supplies hydrogen and OH, but it places them in the wrong locations. So we've got a step. We've got an idea on what we want, but the reagent is wrong. In a synthesis question on the exam, you're getting graded on both how you think about it and the exact answer. Supplying to me H plus and H2O, I look at that and say, you recognize the piece that you needed to add. You didn't know the reagent. That's partial credit. You've shown that you understand something. You just don't have your memorization set down quite yet, which arguably you're probably having a hard time with right now. Okay? That's fine. Okay? So you don't get all the points, you get some of the points. What reagent does work there? How do I get the hydrogen to go to the other position?
Oh, could we?
Won't actually be a peroxide. We could go through an epoxide issue, but we don't know actually how to do the epoxide reaction yet. You actually have a legitimate reagent, sort of peroxide. There's a reagent that needs to come first. No metal. It might be perhaps a bit boring. BH3 adds the hydrogen and the boron in the anti-Markovnikov fashion. Why? Because what are we adding in BH3? We're adding a negative hydrogen. The negative hydrogen will go where? The more positive carbon, which is the one in the middle. That drops the boron at the terminal position. How do I get rid of the boron? That's the peroxide. Okay. I now have the proper reagents to shift that. Getting the idea? Okay, you don't have to be perfect at it, but you get the flow on how we're thinking about it. That's what I want you to be realizing right now. Is that a yes or a no? That's no answer, so that doesn't count.
Under my breath on that.
I feel fuzzy on how this mechanism works for this.
So, there's another issue. I don't understand the mechanism on how that works. Okay? You're really not going to like the answer. Organic chemistry is a one-year course. It is not 2 semesters, it is 1 year. Which means the material we're talking about in second semester, you know from first semester. That's why you passed first semester. Okay? Which then means, am I expected to talk about the mechanism for this reaction if it is a first semester reaction? No. You're responsible for knowing it. So I can't devote time in class to it. Outside of class, absolutely. You could even send me an email and I can even write up a video because everybody loves watching me talk on videos. Okay? Showing what's going on with the mechanism. I can point out pages in the textbook. The mechanism aspect is something that you need to start recognizing and looking up for in the old material. Okay? Which sucks, but you got to do it.
Well, the test you're not going to be looking for the mechanism then, are you?
So good question. Does it make sense for me to test on a mechanism from first semester?
Yes.
No, okay, because that was first semester mechanisms. I expect you to use the reagents. What I will expect you to do are the mechanisms we talk about this semester, because we're adding the mechanisms, the understanding on top of it. So you should not expect to see a mechanism from first semester. You're responsible for knowing the end results. Why do we look at the mechanisms? That tells you stereochemistry, that tells you regiochemistry, that tells you where the products go, what products you get, how many products you get, what's the relationship between the products. All of that comes from understanding the mechanism. Okay? Which gets us to our next point. Are we at our final answer yet? No. I somehow need to hook up our partially positive carbon that we solved for earlier and that partially negative oxygen that we just generated. How can I make sure that those two hook up with each other?
You have to
Substitution reaction. In a substitution reaction, what do we need? 4 things. My students are all required to know this. 4 things. What do we need for the substitution?
negative and positive.
More specific, but yes, we need a negative and a positive.
Nucleophile.
We need a nucleophile. What else do we need? Electrophile, we can split that up a little bit.
Base.
Nope. You're just listing things now. That doesn't count. 4 things you're required to be looking at when you look at a substitution reaction every single time.
Sterics.
Nope.
Stability of the carbocation.
Sterics and stability of the carbocation are getting at the same concept, but you haven't mentioned that concept.
Resonance. Stability.
The substrate. What kind of substrate do I have? Is it a sterically hindered substrate, which then means SN2? Would I form a really stable carbocation? SN1. That's looking at the substrate. You evaluated the substrate to decide that. So we had a nucleophile, we had a substrate. Solvent, which is the crappiest one to ever have to look at, but you do have to look at it every so often. So typically I would save that for my pinky because I don't like gesturing that one.
Leaving group.
The leaving group, which is also part of the substrate. But do we have a good leaving group? Okay. So solvent, we hope and pray that we don't have to worry about it. So let's ignore that. We're actually down to only 3 things we have to worry about. Do I have a good leaving group? And if so, where is it? The bromine is a great leaving group. Why do I not look at the oxygen as a leaving group? Okay, for a couple reasons. One, I need it. It's in my product, so it better not leave. Okay? And number 2, why is oxygen not a good leaving group? We'd be forming hydroxide, which is unstable. Even if we protonated it, we'd then have primary carbocation, not a particularly good structure. Okay? So we have the leaving group. Okay? Do we have the nucleophile? Yes? Where is it? The oxygen. How do we know the oxygen is a nucleophile? What is the frickin' definition of a nucleophile? It's an electron donor. If you're going, well, I don't really remember, guess what you need to do tonight? Memorize that. You need to know those definitions. That is how you can move through organic chemistry without memorizing every single bloody reagent. And if you're concerned, well, that's not that bad, open up the back of the textbook to the appendices. There's a lot more reagents than you have brain cells. Okay? That doesn't quite sound right. That's a bit mean. Okay? There's a lot of the textbook only shows some of them. Let's try that. The textbook only shows some of them. Okay? There are a lot of reagents that go into this. Okay? A lot of reagents. It's going to be hard to memorize them all, so you need to have some idea on how to classify them so you can process. Okay? So your nucleophile is an electron donor. Well, oxygen is partially negative because it's electronegative, so that makes it a decent nucleophile. It also has lone pairs. It's one of the reasons why it's a good nucleophile. Would this reaction go very quickly on its own? Probably not. They're both neutral species. Okay? So I do have a pretty decent positive, and I have a pretty decent partial negative, okay? But I want it to go faster. Because when you come into the lab, what is the very first thought that comes through your mind? When you can leave. Okay? And that's not just you. Everybody, when they go into lab, that's what they're thinking. When can I be done? So I want it to go faster. I make it go faster by doing what? Making them more reactive. Make the positive more positive and make the negative more negative. Can I do anything to really change my positive? Bromine won't react with anything. If I bring in electrons, if anything, that's going to stabilize that positive. So I can't do anything to the positive. Can I do something to make that negative more negative? What can I do? I can remove the hydrogen, making this species acting as an acid, because it needs to get rid of that hydrogen. So what do I need to add? A base. When I add that base, that removes that hydrogen, and that's now not a partial negative. That is a full-fledged negative charge, which is now better than a nucleophile. It's a strong nucleophile because it is formally negatively charged. I know, that was probably what you were like, what are you doing? Okay, there are muscles in there, trust me. Okay. We have a negative charge, which is now a strong nucleophile. The negative is more negative, which means reaction goes faster, I'm done faster, I'm out of the lab. Cool, everything's happy. Make sense? So that was 1, 2, 3, 4, 5 reactions. Okay? You could potentially even argue 6 because we have a 2-stepper there. Okay? You're responsible for that. You're responsible for recognizing where those pieces are and how they process. That is what you're doing with that synthesis activity. Why is the synthesis activity easier? What's that? No, the synthesis activity is not necessarily 2 steps. It can be 3, 4, 5. Those 2 arrows just mean we're doing multiple reactions.
You're not asking for the reagents?
No, I'm actually asking for the reagents. I do want you to know the reagents to do that.
Because you're not taking our starting product and changing it into multiple things.
What are the little cards for? Those are the intermediates. You now have something to jump to. When we solved this synthesis, did we have intermediate structures? No, we had to think of them. That's what you're responsible for. The synthesis activity is baby steps. Admittedly, really large baby steps, but they're still baby steps.
This is how your teacher said how to walk. It's like take big steps.
Yeah. Come on, you can make it across that pit of lava. Okay. Make sense? Ish? All right. How many questions can you expect to be a full synthesis on the exam?
2.
All of them, because you need to know all the reagents. No, come on. 1 probably full synthesis. You might expect multiple choice questions, maybe 1 or 2 multiple choice questions where here's a list of 4 reagents in different orders. Which of those orders gets you to that product? Okay. So varying levels of difficulty. Okay. Questions about that? And then there's an interesting point, Corey. What did you just say?
C.
C. Why did you say C?
That's the most common one that people pick.
All right. So you are one of my former students, so I'm going to call you out for that. That's not true.
You tell us which one.
I tell you which one's the most common multiple choice answer.
That's not okay.
If you read the directions, might be a good idea. Okay. So exam prep. Synthesis activity, we just went through and did that. The homework, if you're doing what you need to be doing for this class, the homework is done. I don't mean the paper homework you're supposed to turn in tomorrow. Friday, close enough. Okay. I mean the online smart work homework. That is done. But we haven't finished talking about it. That's fine. The homework is supposed to be practice, getting you thinking about the material so that when we're talking about it in class, you fix the mistakes you're making in the online homework. It needs to already be done. How many people finished it? Yeah. It's okay. Right? No one's going to do that, but if you want to do well, that's your target. Okay? For those of you that haven't finished, I would actually pull them out, but I can't pull it out once someone has started it. So you can thank the people that already finished it or started it. Chapter 10, we will not cover everything. Okay? Absolutely, that is not going to be on this exam is the carbon nucleophile. Okay, which is your enolate chemistry. So chapter 10, I'm fairly certain 3, 4, 5 are the only ones with enolate chemistry. ignore those questions, I will go back in and add points manually for that.
So still submit it?
So still submit it, okay? Because you need to prove that you did all the other work. But 3, 4, 5, you can skip. If you're on top of it and you think you got it, go ahead and do them. You should be able to do them, okay? Working practice for the exam, okay, or work the practice exam. By Friday, I would say that's done. Okay? Why? Or mostly done. Because then Friday, you can come into office hours and be like, dude, I didn't understand this question. Help me figure it out. You then have the practice exam done. You can spend Saturday and Sunday studying and trying to memorize the reagents. Okay? If you are trying to figure out homework questions or anything else through the weekend, that's not going to set you up good for the exam. Okay? The next part, once you finish the exam, you need to take a look at all the wrong answers. And you need to prove why they're wrong. Explain it using words, structures, whatever you got to do to prove that those answers are wrong. Why? Because I am inherently lazy, and what I will do is very subtly change the question to make one of the wrong answers the right answer. Okay? You need to understand what's going on within it. And if you can prove that with each of those questions, you're really setting yourself up to do well with the exam. The last one, work with other people. Okay? You are not expected to get through this class on your own. If you want to and you can, you are better than many people I've ever talked to. Okay? Most people, to do well, need to talk to somebody else. Okay? Content for the exam, chapters 11, 12, 13, 24, 10, and all of nomenclature, except Chapter 10, enolate chemistry. That's a lot of material, but remember 11 and 12 were review. Most of nomenclature was review. 10 is new content. Most of 24, or sorry, not most of 24. 24 had Diels-Alder, okay, as new content, and then the rest of it was review. 13 is you working questions and synthesis. If there's anything else for me to talk about on it. Okay? Deep breath, awesome. Everybody ready to go? That's what I wanted to hear. Tosylate activation. Right? In all of the chemistry that we've been looking at, we're trying to activate the alcohol. So when we look at our tosyl group, that TS, we already addressed that. That's what this piece is. The next part is what happens when we change it. If this is now OH, what's the most reactive thing? The H. Why is the H the most reactive positive?
Because the electronegativity of the oxygen. Sulfur.
But this sulfur has 3 oxygens. So why is the sulfur not more reactive than the hydrogen?
Because it's more electronegative than the hydrogen.
Say it again. Resonance. Why? Resonance. What happens when we remove the hydrogen?
Resonance stabilizes.
I have a resonance stabilized anion. That is why the hydrogen is more reactive. If I have something attack the sulfur, I actually lose resonance. Okay? What happens if I go through and instead of having an OH, I have a halogen? It's usually chloride, so I guess I should be. Can it act as an acid? No. Okay, there's no hydrogen there. Okay, so what's the most reactive thing here? Can the chloride donate electrons? How many bonds can chloride have? 1. How many bonds does it currently have? 1. Can it donate electrons? No. Chloride's not reactive. So we can look at the oxygens. Could the oxygens donate electrons? How many bonds does oxygen want to have? 2. How many bonds do they currently have? 2. Does oxygen want to donate its electrons? Nope. Try again. So the sulfurs are partially positive, 2 electronegative oxygens, and the chlorine, all pulling electron density away, making the sulfur an excellent electrophile. Okay. What would be a decent nucleophile? The oxygen saved from our alcohol can donate electrons in. We can kick out our chloride as a leaving group. And we end up with this big nasty structure. Whoops, not necessarily hydrogen. Does oxygen want to be positive? No. What can it do? It can take electrons from the hydrogen. So we ditch the hydrogen and we end up with this big old nasty structure. Did we change the sulfur being partially positive? Not really. It's a little bit less positive because it's oxygen versus chlorine, but it's still really positive. So what happens to the electrons on the oxygen? They start to get sucked towards the sulfur, but then the carbon becomes, or sorry, the oxygen becomes positive. Does oxygen want to be positive? So what does it do? It says, screw you, carbon, I'm taking them from you. Which then means what happens to the carbon? Partially positive, making it an electrophile. And we can have a nucleophilic attack. That nucleophilic attack is coming from the backside. We're seeing an SN2 type mechanism. At this stage, we would get inversion in stereochemistry. When we first react the alcohol with the tosylate, or the toluene sulfonic acid, or sorry, let's just say tosylate. Right. Do I see any stereochemistry change about the carbon? Why not? Does the carbon react when the alcohol structure, when this structure reacts with that structure? No, the carbon didn't do anything. So what should happen to its stereochemistry? Absolutely nothing. Kind of makes sense? Hi. Question? Okay. Kind of the last one on our list. Taking a look in that upper right-hand corner, and partially down there, but a little bit less so. What was special about that upper right-hand corner? What's that functional group? Ether. Not in the upper right-hand corner. It's only an ether. Okay. What is special about our ethers? They're a good solvent. Why would we use them as a good solvent? They don't react with anything. Of course, you know what the next question is. My little petulant 5-year-old. Why? What was that? It's too bulky. Right? Those carbon structures in any ether will block anything getting near that oxygen, which is one of the reasons why our ethers tend to be insoluble in water and really good as organic solvents because they dissolve organic compounds. Okay? So the question then becomes is how do we make these? Okay? So there's a couple things we can do, or a couple things we need to do. We need a good leaving group. So if I'm starting with an alcohol, how can I turn that into a good leaving group? Deprotonate it? Give it an extra proton, as in protonate it, yes, and it turns into water as a great leaving group. Then what could happen? A second molecule can come in, backside attack, and kick it out. So that's one method. In that first method, do I have a strong nucleophile? So I protonated it, and I now want to react that with another alcohol. Should that alcohol be a strong nucleophile? How would I know it's strong? What charge? Should it be a strong nucleophile or a weak nucleophile? Why does it need to be weak? Huh? The makes a strong, and you didn't quite finish that statement either, but the makes a strong already makes me say no. Might have to finish it to defend your answer, but. What if it's strong? I have a negatively charged species. Negatively charged species act as nucleophiles and bases. What did we do in that very first step? We made it a really good acid. If I add a strong nucleophile, I'm likely adding a strong base. I get the acid-base reaction. I don't get the product I want. So if I'm going to go through and activate that by making it a good leaving group with water as a leaving group, I cannot use the strong nucleophile. Instead, I will have to use the weak one,
Which means not charged.
not charged. I still need something that can easily be removed. What's the easiest to remove atom? Hydrogen. So I get my nucleophilic attack. I can kick out my leaving group. My oxygen would be positively charged. That's bad, so what has to happen? We can remove the hydrogen. Why can I remove the hydrogen? H plus can stabilize the charge better than the oxygen. Okay? So that is one possible synthesis. Okay? We make the leaving group really, really good. Okay? In that case, we added an acid. We could have turned it into a halide. That would have been equally valid. If we turned it into a halide, what's the extra benefit? So give me a reagent that would allow me to turn that alcohol into a, into a halide. What's that? PBr3. Actually, I do want to do that. What's the benefit of turning that into PBr3, or turning that into a halide? What can I now react it with?
Strong base or nucleophile.
So remember what we're trying to do. We're trying to make an ether, so it should be a strong nucleophile, or it should be a nucleophile. Why would I prefer the strong nucleophile now?
Faster.
It's faster. I can speed up the reaction now by going with a stronger nucleophile. Okay? So depending on the reagent conditions we're running under, we can get different products. Okay? Could I have just outright made the alcohol a good nucleophile? How could I make the alcohol a good nucleophile? Define nucleophile. It's an electron donor. Characteristic of an electron donor is what? A negative charge if it's strong. How do I make the alcohol, our structure in the upper left, a strong nucleophile? Get rid of the hydrogen. How do I get rid of the hydrogen? I add a strong base. The strong base gets rid of the hydrogen, and I now have my strong nucleophile. What do I need to react the strong nucleophile with? Lots of words describe this structure. Okay. Halide is one answer. Remember, I wasn't super specific as to what's on those. So I can describe it as a halide. What else could I describe it as? What's that? I'll accept substrate. What did we say we made the alcohol? A nucleophile. What reacts with nucleophiles? An electrophile. Okay. Recognizing what an electrophile is, what a nucleophile is, and how they can potentially react is super, super important. You need that. Okay. Or at least you need that when I teach you it. If you don't want to listen to me, then you don't need to know that information. Somebody will make you do something else. Okay? Questions? Okay. If we go through and do it, the make a good nucleophile, it's known as the Williamson Ether synthesis. You might see that pop up. I think it's dumb to memorize a name. Okay? So if we add a strong base, we can go through and get our potential ether out of that. Okay, so let's take a look at a couple syntheses. Okay, KOH to ethanol, so more specific here, to form our ethoxide, our negatively charged strong nucleophile. We can react that with our alcohol, or sorry, our electrophile, the ethyl bromide, and we get our ether. Okay? So guess what I want you to do now? Here are two ethers. Okay? mTBE, any ideas? What is this piece? That's a methyl. What is this piece? Tert-butyl. What does it mean when I have an oxygen between two carbons? Ether. Methyl, tert, butyl, ether, mTBE. This one, anisole, because this piece is a common name. Sorry, you just need to know that, actually. There really is no connection back to anisole. Anisole is just a straight-up common name for that compound. Okay? So let's do it this way. Right side of the classroom, left side of the classroom. You guys are going to be doing different ones. Okay? Whoever shouts out on that side which side they want to do. Okay. Right side is doing mTBE, left side is doing anisole. Lucky you. So it's going to be the same issue in both cases. Okay? The structure is different, but you end up with the same issue. Okay. So what we're going to look at when we look at mTBE, okay, is the first synthesis step that most people try and go through and do. Okay? So we look at mTBE, and we want to break a bond, think backwards, right? Most people picked that one. Okay? And I would guess that in the other one, most people picked that one. Is that true? Why? It's really stupid. This is one of the reasons why organic chemistry becomes difficult. I would argue it has nothing to do with benzene. It has nothing to do with chemistry.
You need to turn it into a nucleophile. And
How many of you read right to left? Right to left. How many of you read right to left?
Nobody?
Nobody. When you looked at these structures, how did you read them?
Left to right.
Left to right. Which bond did you break? The one that's on the left-hand side. What if I flip the structure over? Okay. Then you all solve the other one because it showed up first. One of those bonds works, one of them does not. This is one of the complications when it comes up with synthesis. So let's take a look at the mTBE and break that. Okay. The way the groups that I saw looking at this went with this structure. Said, okay, I'm going to break that bond, and then I would have my oxygen over here. That would be my negative. Okay. I can't have a negative oxygen outright, so I'm going to put the hydrogen on it. So my first step will be add the base. What does the base do? Reacts with the alcohol to give me the negatively charged oxygen with my CH3 on it. What does that negatively charged oxygen then need to react with? In step 2, okay, my halide. The negative comes in, kicks out the bromide, and what do I end up with? Well, I'd have 3 carbons, yeah. The center carbon has an oxygen attached to it, yeah, and it has a methyl group. Anybody debate that what I've drawn produces that? So just what I've drawn, we'll decide if it's valid or not in a second. Okay. What I've got drawn is perfectly valid. Now the question becomes, is that a good synthesis? I'm taking a strong nucleophile, which then immediately sends off red flags in your head that it's what type of a mechanism? SN2, which means backside attack, primary substrates. That is a strong nucleophile doing a backside attack on a tertiary substrate. What is the product of this reaction? And as a hint, it is not mTBE. This synthesis does result in a product. You generate the double bond. Negatively charged species can act as nucleophiles and as bases. If it can't act as a nucleophile due to sterics, what does it act as? A base, and I get the elimination product, not the substitution. The exact same type of issue pops up over here, except we don't even get the elimination, we'd get no reaction. And that's only going to happen if I break the rightmost bond. So believe it or not, I set up mTBE people to fail, and I set up the anisole people to succeed. So that's what you get for jumping in first. Okay. So let's come up with the proper synthesis. What does that mean I need to do? I need to break the other side of this. I need to stabilize that negative by putting in the hydrogen. My step would be add base. This is going to result in, because I'm lazy, I'm going to write out the name, T-butoxide. I then follow that up with my halide. Now I end up with MTBE. Anybody have an issue with T-butoxide?
It has a charge on it.
It should. We added a base to remove the hydrogen.
Oh. I thought that was your end product.
T-butoxide is typically our classic base because it's bulky. It can't act as a very good nucleophile. So we would do the elimination. Do I have anything to eliminate N-methyl bromide? No. So there is only the substitution. Okay? I don't have to worry about an elimination issue in that case. Okay? So synthesis is not just match structures, match reagents, and work. We then also have to evaluate, does that synthesis work? Okay? And yeah, if you're going, this is stupidly difficult, it is. Welcome to organic chemistry. This is also why it's really fun. Right? Because the instant you get one solved, beginning to end, all by yourself, there's a little bit of like pride, like hell yeah, I kick butt, I know what I'm doing. And then you move on to the next one and you get it wrong. But eventually you get it right. Right? So it's constantly looking for those structures, processing those pieces, and working your way through it. Questions? Okay. Internal ethers, also known as epoxides. Okay, you have seen how to make an epoxide before. We start with an alkene and we add mCPBA. It's on the slide. Trying to be nice. Okay. You add mCPBA, we do goofy 5-arrow mechanism, and we get our epoxide product. There's another way to go through and do it. Okay, starting with an alkene. We'll add bromine. What's the product of that reaction?
You get bromine. You get 3-member ring of bromine, and then you get that ring opens up to have 2 bromines.
Okay, so we're hearing a couple things coming out of this. We're hearing reference to a 3-membered ring with bromine. What is special about that, or what is the point of that structure?
It's just a transition state.
It's an intermediate.
But I thought it didn't actually exist.
Let's just call it an intermediate. If you want, we can discuss that later.
Okay.
Okay. We have an intermediate in the course of the reaction. Because there's no other nucleophile other than the bromide, the other bromide can come in, do a backside attack, and we would have 2 bromines attached to our structure. We've drawn the product. As soon as we've drawn the product, we should immediately be thinking, do I have stereocenters? I do potentially have stereocenters. I have to understand how the mechanism worked to get those stereocenters. Because it was a backside attack, one of those bromines is dashed. The other one is wedged. Is that it?
There's another product.
There's another product. I have the enantiomer. Why do I have the enantiomer? Because I'm reacting in an addition type fashion. The addition type fashions will always produce 2 products. If I have stereocenters, that's when I have the potential for enantiomers or diastereomers. And so I do end up getting the enantiomer for this product, or for this structure. It does not. Okay? So we've got our first product. Oh, man. What the heck was I doing there? I gave you the intermediate. Oh. Close your eyes. So that could put 2 bromines on. Okay? But if we look at our product, do we have 2 bromines? No. We actually have an oxygen in there. Can I get an oxygen in at the same time I get the bromine on?
I just erased it.
Yes, I can, by adding water. I now have a competing nucleophile, bromide versus water. Which is the stronger nucleophile? Those from first semester all know the answer. It is bromide. Bromide is the stronger nucleophile because it is charged. How do I get the water to attack then if bromide's the stronger nucleophile? Concentration. I limit the concentration of the bromine and I have a very high concentration of the water. I can do a concentration force for the water being substituted in instead of the bromine. Stop it, slides. Okay. The result, we ignore that part there, I just scratched out, is that we would get still that trans product where one of those is now the alcohol and not the bromide. Okay. How can I then get to the final product? You've all been looking at the slides, so you can tell me. Strong base, thank you. How does the strong base work to get us the epoxide? Okay, strong base comes in, removes the hydrogen. What happens to the oxygen? Becomes negatively charged. What does that negative charge need to find? A positive. Where's there a positive? Positive carbon with the bromine, and we can kick out the bromide leaving group. And we would end up with the epoxide. Does anybody have a problem with this synthesis?
It just seems like
Good.
It seems like that's just like the, I don't know, I don't see that actually working without.
Why?
Because I don't see, you have the prime bromine to leave.
Uh-uh.
No?
Try again.
Oxygen.
So the hydrogen won't stay with the oxygen because we add a strong base. The strong base will by definition take the hydrogen off. That is the most acidic hydrogen in the structure because it's attached to an electronegative element. Okay, so that's how we get rid of that.
So a strong base could attack the carbon instead?
So it could theoretically in a substitution type fashion, but what can we do to limit that?
Concentration?
How can I make sure the base does not act as a nucleophile? What is the difference between a base and a nucleophile?
Big base.
Bases can be big, nucleophiles must be small. So the strong base I'll add should be a bulky base so it can't do the substitution. So valid argument, but I just fixed it. Try again.
That,
Everybody loves this from first semester. The hybridization of that atom is? An sp3 atom has what bond angle? 109.5 for sp3. What is the bond angle in an equilateral triangle? 60. Does anybody have a problem with this synthesis?
so you get ring straight.
We are starting with an sp3 atom with a 109-degree angle, and somehow or another that 109-degree angle is saying, let me just do this and form a bond. What's forcing it to do that? Nothing is forcing it to do that. We're just kind of ending up there. Turns out our cyclopropyl-esque type rings have some kind of internal stabilization. We'll just kind of leave it at that. How do we know this reaction works? Joe Bob went into the lab. Guess what happened? It happened. That's how we know it happened. What is the mechanism behind that? We really only have one explanation. That has to somehow share electrons back. There is no other choice. If the bromine left first, what do we have? Carbocation, which is positive charge. Yep, keep going. Give me the fancy name. An electrophile and a negatively charged oxygen is a nucleophile. I can get two of those reacting with each other. Okay, and I get a polymer instead. For that oxygen to attack solely back, the bromine still has to be present at the same time. That's how it has to go. Okay. Another little piece of information that could help us with this. What if somehow, okay, and then everybody flips out. So let's pretend none of this happened over here. Okay, none of that happened. And what we got here was actually this guy. Somehow started with that. What happens when I add the strong base? Hydrogen gets taken away. And I form my negatively charged oxygen. Now what happens?
You can't do a backside attack because it's on the same side.
It can't do a backside attack because they're both wedged. There's no way for it to do that backside attack, which means no epoxide product. It stops right there, I'm done. Why does that help us believe that it has to be doing a backside attack mechanism? Because if it wasn't backside attack, the bromine leaves and I would have
You would have an epoxide after.
carbocation where the oxygen could then share electrons with that positive charge and I could form the ring. Okay? So it can't possibly be an SN1 reaction because this reagent does not make the epoxide. Okay? So we can use our experimental evidence to help us support those mechanistic answers. Kind of make sense? Okay. Unfortunately, that's all you get. Okay. Epoxides are made by reacting with alkenes. What's our issue with alkenes? Yeah, they're nucleophiles and electrophiles. Keep going. I want more issues with alkenes. Or really pi bonds, if I'm more specific.
They're pretty stable.
Okay, if this table is the sigma bond, where's the pi bond?
Up above it.
Above it and below it, which means the epoxide can form above it or below it. I get two products when I run an epoxide reaction if I'm not careful with how it goes through and processes. Right? So ideally, I would come up with a fancy reagent to prevent that. So this is what this is showing. If we go through and do an epoxide with this alkene, we get either product. The relationship between those two products should be enantiomers. That sucks. We don't like that. Boo. Thank you. Some guy named Sharpless invented a new reagent. This reagent forces only one of those enantiomeric products. Okay? Anybody want to memorize the titanium tetraisopropoxide plus the plus DET minus DET? No, good. I don't want to memorize it either. Okay, so don't worry about it. I just want you to be aware that there are ways that we can force one product over the other. Okay, it requires special reagents. The one question I will ask, what does plus and minus mean? No, it has nothing to do with charge. It is the optical rotation. So one of those is R and one of those is S? The plus is R, plus is S. Way to take it to the next level. Or the minus is S? No. R and S have nothing to do with plus and minus. Two separate systems. R and S is looking at the structure and assigning the chirality of the whole steering wheel lowest priority away from you. Plus minus, I go into the lab, I stick it into an instrument, the instrument says it's plus. That's plus minus. Two entirely different systems. Sometimes they overlap, sometimes they don't. Okay. Why epoxides? We do get natural epoxides. They do show up as biomolecules. Lots of cool things can happen with them depending on their condition. So if we take a look at this reagent, okay, I'm going to focus on the one on the left here. What is the relationship between the two structures I've got drawn? Same molecule, all I'm doing is rotating it so the oxygen is either coming at you or it's in the plane of the board. Why would I do that? So we can see different viewpoints on the structure depending on what we're looking at. If we're under neutral or basic conditions, what kind of nucleophile are we typically adding? Strong. Basic conditions remove hydrogens. We have a negatively charged species. That strong nucleophile is going to attack where? Which position?
Substituted.
So we have red and we have blue.
Red.
Whoops. So I've got to vote for red. I got to vote for blue. Yes, we can get a fight. Start arm wrestling. A second vote for blue. What's going on? Strong nucleophile. When do we see strong nucleophiles? SN2 directions. And in SN2 mechanisms, what happens to our nucleophile? Backside attack. To do a backside attack, what needs to be on the backside? Nothing. Which of those two, red or blue, has more nothing on the backside? Blue. So what ends up happening under neutral or basic conditions? The nucleophile attacks the blue position. There's now too many bonds at the blue position, so what happens? It opens the ring by shuttling electrons to the oxygen. So our oxygen does act as a leaving group. So we're doing what type of a reaction here? It's an SN2. A lot of people tend to panic because you say, where does the leaving group leave to? Usually it leaves out into solution. I get two things. Is it leaving into solution? Why not? It's still attached to the rest of the structure. That doesn't change it. It's still an SN2 reaction. It's just an internal SN2 reaction, or a partially internal SN2 reaction. Okay? So the result is that I get it coming in from the back side. The OH, or the oxygen, which is later protonated, is up. In this case, the nucleophile text is down there. If I looked at the other direction of the epoxide, that's the other product I would get. Kind of vaguely? Fortunately, that's all I'm going to accept. Acidic conditions, what happens? Under acidic conditions, what's the most reactive thing? The acid. So what do I got to do first? Fix the acid. The acid is reacted because it is positively charged. What do I need to stabilize that positive charge? Electrons. Where do I have electrons in the epoxide? The oxygen. So the very first thing that happens, the oxygen donates its electrons to the hydrogen. Okay. The result is that I now have one of the above. The result is that I now have that hydrogen, the oxygen is positively charged. Does the oxygen want to be positive? No. So what is the oxygen trying to do? Leave. It's going to start taking electrons from somewhere. It can take them from the hydrogen, that goes backwards. Or it can take it from the carbons. Which one of those carbons is it more likely to take electrons from? The more substituted, because then the more substituted is the more stable carbocation. So the oxygen is already saying, screw you, carbon, I'm taking it. Okay, it can't formally take it because the carbon says, no, I still need to own those. So what helps break that bond? Now I have a nucleophile come in. Where's the nucleophile coming in from? The backside and we don't even need to worry about that. What is different about this? Where is the nucleophile now? It's on the more substituted position. And everybody goes, oh my God, it's an exception. No, it's not an exception. Follow the reagents. The reagents lead you to those steps. Okay? That's why we look at the mechanism. That's why we look for positives and negatives. It irritates me when people say, oh, there's a rule. Let's memorize some rule. The rule are those 5 things that we talk about in the lab, starting with charge, size of the atom holding the charge, electronegativity of the atom holding the charge, resonance, how does the charge move through the molecule, also known as size of the molecule, an inductive effect. How are those electrons pulled into the structure via electronegativity? And the last one, hybridization effects is really the last thing. It's really our O-carp, okay? Just because there are other things that show up in there. Do you need to know those? Yes, that's how we predicted how these things react and come together, okay? Which then gets us to our very final thing. This is the summary of all of the epoxide stuff. I know we're done, just give me a sec. All of our epoxides are now up here, summarized nice and neatly. Okay. You could go through and take a look at the possible products coming out of this reaction, which summarizes everything, okay, that we've talked about, which then takes us to the nitrogen amines from chapter 10. Guess what? Class is over, which means it's not on the test. So we'll pull the nitrogens and the enolates from the exam. I am actually going to ask you to do the nitrogen homework, though. Okay? Mainly because I don't know what questions those are. So when it comes to the homework, chapter 10, 3, 4, 5, you don't have to answer every other question in the homework you need to answer. The written